Everyone. For those who weren't here yesterday, that's a link to all the references I'll be talking about and the exercises for the tutorials. Yesterday we talked about 2-point amplitudes and 3-point amplitudes in nice, safe space-times, which were nicely divided into flat in and out regions, and then there was a nice wave in the middle, and we scattered off the wave and stuff happened. I talked a bit about radiation, but I didn't get a chance to talk about radiation reaction. I'm going to skip it. If you want to talk to me about it in the break, please do. But basically, those are the diagrams for radiation reaction if you're interested. The first one we talked about yesterday, it's just geodesic motion. There's radiation, and in some sense, there's reaction. Right? It's a kind of a self-force contribution. It's got a loop in it. Yeah, I can talk about it later on, but basically you need both. You can't ignore one or the other. If you do, you just get some divergent mess, which is completely nonsensical. Has hyperclassical terms, has infrared divergences. It's rubbish. You got the two together, everything's fine. Right? Classical radiation reaction. All right, that's all I want to say. Okay, so yeah, yesterday we played it a bit safe, and now we're going to go and do something a bit mental, which is the perturbative approach. And yeah, right. So what is the perturbative approach? The idea is to express tree-level amplitudes in a way which allows you to calculate them even when you don't have an S matrix. So it's one of those things where there's a lot of writing of the definitions and it looks really complicated and confusing, but then we'll do examples and it's easy. Right, so here's the definition. Three amplitudes are multi-linear pieces of S classical action. Evaluated on, sorry, this is a lot of writing. Recursively? What is recursively? By degree. Yes, I have decided spelling. Recursively constructed solutions of the equations of motion. Right. So, what does this weird definition do? I'll give you an example. This definition of amplitudes trades like Feynman diagram calculations for kind of functional derivative calculations, right? So you write out explicitly what you do in the case of lambda phi cubed theory in order to calculate a tree level action. So this is the statement. Endpoint amplitude at tree level is given by evaluated on something called phi nk. Tell you what it is. Get a bunch of derivatives. And set all those derivatives 0. Okay, so before we get into details, there's going to be some dependence on these parameters epsilon. I'm differentiating with respect to them. I'm setting them to 0. Right, I'm just picking out some kind of piece of the classical action. That'll tell you what this thing is. Squared. So this thing phi nk solves the equations of motion of lambda phi cubed theory, right? There's the kinetic bit. It's just the derivative of the interaction, yeah. Factors of 3, blah blah. Right? And the k okay. Solve that toward a k. And powers of lambda. Right, so perturbation theory in lambda, you can do that. And my initial condition is that phi n 0 is just a collection of free fields. Right. So what's going on? I'm scattering a bunch of things with momentum k1 to kn. Yeah. I construct this solution of the classical equation of motion with this initial condition, if you like. You plug it into the classical action and you pull out a particular term proportional to these epsilons. And that will turn out to be the tree-level S matrix L.
This is in position space.
And this is in position space, yes. But of course, the amplitude will be in position space, yes. So you have to do the integrals. Yeah. But I mean, this is just exponentials and propagators. So the only integrals that you do are the usual integrals. So you do them explicitly. Yeah. Okay. So references for this. This is, seemingly one of those things that was known to the ancients, and is not particularly user-friendly, right? So this, asking you to take on trust, go away and play with it. And it's like, oh, it'll work, right? Okay. It's very much a kind of shut up and calculate kind of thing, right? Just go and do it, and everything will be fine. And you'll realize if you get into it, that this is absolutely not the way that you'd ever want to calculate tree level amplitudes in phi cubed theory, or in QED, or in anything else, right? It's a lot of work. But the point is, right, that this kind of definition of what you mean by an amplitude doesn't refer to an S matrix. So, oh, 83, 87. All right, so if there's no S matrix, or you're not quite sure what the S matrix is, or you think something goes wrong, maybe there's a horizon, there's a black hole, things aren't asymptotically flat, blah, blah, blah. Well, you still just take your action, construct the appropriate solution, plug it in, and the things that fall out have exactly the same kind of information content as you would expect of a scattering amplitude.
Condition would change potentially, right?
The boundary condition would potentially change, yes, exactly. Yeah, it would. So there's a lot of freedom and kind of flexibility in this. Yeah.
But this boundary condition is appropriate for asymptotically Minkowski.
Yes. But yeah, absolutely. Very good. Okay. So all we're going to do, find it, is do some examples of this to show you how it works. This examples pulled from the literature. All right. Any questions?
Yeah. How would you go about proving this? Like,
you go and look at these awful papers, and dig your way through them. Really, it's literally just I would write down the path integral, right? Expand it, just keeping the tree level pieces, and basically work backwards, knowing what you're aiming for. It's not particularly fun, but
there's a connection to something. Like, this is running. This is a statement that this classical solution is a generating function of tree amplitudes.
Yeah.
Right, so this is just working that backwards.
Working that backwards, yes. Yeah.
Is there any constraint for the kind of theories you can describe with this?
Good question. I don't know of a situation where it doesn't spit out something reasonable. Yeah, good. Let's try and break it. Yeah.
What about fermions? How do you order the derivative?
Oh. Yeah.
So when there are fermions, usually people use supersymmetry, right, for perturbators.
Yeah.
So they use theories that supersymmetry. How they include fermions in the story.
Second.
That's how they include fermions.
So yeah, there's definitely have to.
I mean, it's
There is a way of just extending
there's a way of saying this.
to fermions. I never do this with fermions.
Won't go wrong though. I mean, if you just use this one, I mean, you got the initial condition, you got the equation of motion, you just solve it.
It's an overall sign wrong, but you know, provided that you're not adding different things together, who cares about the overall sign, right?
Well, why do you get the sign wrong?
If there's complications, I don't think they're particularly severe. Right? For the cases that we're going to be looking at, it's fairly easy to see how to generalize it to
I mean,
fermions.
there's nothing here saying what's in and out.
So. So if you want to calculate, as we did yesterday, like 2 points, we'll start there on some curved background. Right, so that is, you know, 1-to-1 GeoD6 memory, or maybe you want to do 0-to-2 pair production on the background. Then the perturbative method says, do the following. Evaluate the quadratic part of the action on a solution of the equations of motion. So, you know, I'm thinking about some scalar field, for example, right? So I'm thinking about the 1-to-1 amplitude or the 0-to-2 amplitude for the scalar field. I look at that part of the action which is quadratic in the scalar. That's just, you know, the kinetic bit. I evaluate that on particular solutions of the wave equation. So, you know, 1/√g d mu g mu d mu phi plus m squared phi equals 0 with, you know, appropriate boundary conditions to describe 1-to-1 or 2-to-2, whatever I'm interested in. Okay. Let's do examples, and then it'll become clear that this really does work. Okay, so let's do CFD. This is, of course, Witten 98 paper. So imagine I've got scalars on ADS of some fixed background. So I've got a metric ds squared, dr squared, x squared over r squared. Boundaries are 0. Okay. What we usually mean by like a 2-point amplitude in ADS, we mean boundary to boundary correlator, for example. So I'm just literally repeating what's in Witten's paper. He never talks about perturbana in that paper. It's exactly what he's doing. I want to put a scalar in this space-time. So I can construct a solution of the wave equation. And that looks something like this. Let's call it phi. Let's give it a little label J because I'm going to need 2 of them. And it looks like, roughly speaking, the x d gamma plus squared, some conformal weight delta, and then there's some phi j, which lives on the boundary, and the missing delta space there. Okay. can go away, you can do that. Okay.
What is D?
Sorry.
Okay.
Yeah, so we're doing D+1. Yeah, apologies. Okay, very good. Okay, so we want to take this guy. And
Denominator.
so again, sorry.
Your denominator, is that R squared? Eventually weird.
It does look dimensionally weird, doesn't it? That can't be right. Let's see on it.
And the other, what's it? X. R squared? That's zero.
Right. Hang on.
Oh, why?
That's a Y. That's a Y. I'm being an idiot. Too early. That's a function of R and X. That's an integral of a Y to the boundary. Thank you, Donald. Still not getting a whiskey. Right, so what are the solutions of the wave equation describe? There's the boundary at R equals 0, and I've drawn it so it looks like R equals infinity, which is great. And there's some source there on the boundary, and of course this guy is just propagating it into the bulk. So that gives me phi j there. All right. Okay, very good. So we're supposed to evaluate this on the quadratic part of the action. Let's think about that. So what do the quadratic parts of our actions look like? And here I'm going to play fast and loose a little bit. Very, very roughly, if I'm talking about a scalar field, right? Quadratic part of the action will look like d phi by d phi with an m squared. Who cares? Right? Integrate by parts. Right? I'm evaluating this thing on a solution of the equation of motion, and that last term is 0. Boom. So that the whole quadratic part is just a boundary term, right? Whether it's in QED, gravity, Yang Mills, whatever. Boundary term. Whether it's in flat space, curved space, blah, blah. Yeah. So you're always evaluating a boundary term. Okay. We'll take two of these solutions that I've constructed, right? Phi 1 and phi 2, and weight them with epsilon 1 and epsilon 2. Then you just pick out, my epsilons keep changing, sorry. You pick out that bit of the action, which is linear in both epsilon 1 and epsilon 2. Right? It's the kind of perturbative instruction. Right. Then boundaries R equals 0. Powers of R all over the place, and there's powers downstairs. There's parts of R in the measures and what have you. So we're probably going to have to take a limit, but that's fine. We can do that. So looking at the limit as R goes to 0, then you've got d to the d of x. You get some factor of r to the minus d by 2 r dr by 1. Yeah, or the limit r goes to 0. So there's your boundary term. You pick out the bit which has phi 2 and phi 1 in it. Measure, you've got the derivative. Got the explicit expression for the wave function over there. Forward with the details. Turn the handle. Make it this bit. Yeah. turn the handle, and what pops out is. Two intervals over x and y, and then phi2 of x, phi1 of y, boom, yeah, x minus y. All that stuff, which I just rubbed off the board inconveniently, all the R stuff in the denominator goes away, of course, and what's left is the correlator FT. So what's been spat back at you by the perturbator is something which x phi1 and phi2, you've gone through the bulk to get this, to do this calculation, right? We constructed the solution of the wave equation in the bulk. Of course, what is spat out is just a correlator on the boundary between phi1 and phi2. Right? Thanks.
So just one dumb question. Each one of these phi's is an integral over the space,
Yeah.
and you have the boundary, which is the other phi, right? So you have two of them here.
Yeah.
So then I guess you have integrated one of them, and you wind up with only two of these measures. So just counting integrals, you have 1, 2, 3, and there are two there.
Yeah,
So is it, you integrated one with all of the R behavior, or
Yeah,
what happened there?
exactly. Yeah. So one of the, let's see. So the denominators combine subtly with like the R go to zero limit is a little bit careful. That kills one of the integrals for you. That localizes one of the integrals onto the boundary. Exactly. Yeah. And these two that are left are just the ones which joined onto the boundary. Yeah.
There's this approach called heat kernel approach, I think, and curved, curved the housing related approach using the.
Oh, good question. I don't know a lot about it, but I know there was a paper a few days ago about this, I think, and it's in my to read list. So I don't know. Sorry. Clearly you already know more about it than I do. Apologies. All right. Good. Anything else? Yeah.
Is there any results regarding, let's say, unitarity or anything like that? Like for the S matrix, the usual way we define it, we know a bunch of properties. This way, are there some properties like this that like it looks like there's a path for saying some stuff about safety correlators, for instance, or in a unified language with amplitudes?
Yeah. Are there general statements about unitarity and stuff? Not entirely sure, because you want to use this in the next example in situations where maybe you don't have unitarity. And want to evade that problem and calculate something. Maybe a bit clearer after the next example.
So far, this is also tree.
Oh, this is really true, yeah, so far, yeah. If you want to do one loop, then you replace evaluate the classical action on multilinear pieces, blah, 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 with evaluate on the one loop effective action. But, yeah, we'll come to effective action. But again, you would not want to do the calculation this way unless you have to. So this is now, we're only talking together. All right. Next example. So I've taken this wholesale from a paper by Timadamo, Andrea Stoffoli, and Piotr Turkin, none of whom are here. Oh, good. Excellent, I can get it wrong. Wrong. So here's the situation. Here's the black hole. Still can't spell Schwarzschild. There we go. Idea, there's no S matrix at the horizon, etc. But I mean, should that really be a problem? If I'm very far away from the black hole, right, I should still be able to like scatter something. if I want to, right? There's nothing physically wrong with that. Okay, but I don't have an S matrix, so what do I do? Don't know why it's going that way, by the way. No. So. So we're going to consider scattering some generic stationary space-time function of x. dt is killing. Yep, Schwarzschild being the typical example. More generally, the idea is that this correction h here is generated by some mass distribution, which is over here, right? And we are interested in doing scattering at large distance. Okay. Exactly the same things in the ADS example, right? We're looking at one-to-one. So we're going to evaluate the 2-point amplitude. Quadratic part of the action, I'm going to say evaluate the amplitude as the quadratic part of the action. Evaluate on certain classical solutions. Once again, the classical part of the action, M for manifold, not mass, is some boundary. So it's going to be ds. It's going to be square root of whatever the induced metric is on that boundary. And it's going to look something like this. Okay. In and out are like the phi 1 and phi 2. Well, the thing is, in Schwarzschild, we have two boundaries. You've got the boundary off at infinity, nice, and you've got the horizon, which is near. Right? Alternative approach is quite flexible. You just choose what boundary you want to evaluate this on. But we're just going to ignore the horizon. We're going to evaluate this guy on the boundary at infinity. Right? Because we're imagining the situation where we're doing large distance scattering, so we shouldn't really be sensitive to what's going on the horizon. And of course, the idea is that somewhere in these wave functions, or the solutions of the equations of motion, what they should really have in them is a wave packet, right? Which is sufficiently nicely defined such that, you know, it doesn't spread out too quickly and we don't get big effects from the horizon. But we're not going to write the wave packets explicitly. Okay, but that's the underlying assumption, which, you know, is supposed to let you drop the contribution from the horizon. Yeah, I'll be very willing. Go with it.
Right.
Yeah.
Maybe I'm just not hearing the music or something, but where did you get this formula from?
So yeah, sorry. So there's the quadratic part of the action, right? Yeah. I integrate by parts. That d mu shifts. I just get the wave equation. It's dead. So the only thing which survives is the boundary term, and I've stupidly doubled my notation up. And for the back, what over the boundary metric is, I'm writing h, which doesn't help at all. All right. So you got ds dot d phi. Like that. Yeah.
So it's like sorry.
Yes, it's literally just integrating by parts, but keeping the boundary term because it survives. Yeah, sorry. Let's think of h as the induced metric at the infinity rather than some kind of perturbation, because we're treating g as, you know, some exact thing. We're not expanding in powers of kappa h or anything like that. Sorry.
I know that you don't want to write the wave functions, but these wave functions contain information about both also they have to somehow tell you that the horizon, that you are not considering that part. So what do they depend on? What are the parameters.
So they depend on whatever, any parameters putting in the metric. And they're going to depend on some kind of impact parameter, right? Such that that impact parameter, I don't know, however you want to draw it or define it, some B, that is very large compared to the scales at which this mass distribution lives. Right? So you're far away.
And then we see the account horizon effects and the interesting.
Good luck with that. Yeah, it would be really cool to do this. It would. I'm not doing it. Very good.
What is the icona?
Again?
What is the icona limit?
I'm not done yet. Cool your jets. I'll get there. I'll get there. So, right, the iconal bit. So, the idea is we just look at these solutions first. The incoming guy. No, hang on. Sorry. That's right. So what is the boundary? The boundary is that R equals infinity. Which means that the expression that we get out for the amplitude is, well, you know, the thing which contains the same kind of information as the amplitude is going to have an integral over all time in it, right? That's not what we normally have. We normally think of evaluating at t equals plus infinity and minus infinity. But now we're integrating over time, and we've got a limit as r goes to infinity. An integral over the sphere at infinity. R squared is spherical coordinates. I assume, for the sake of writing it down, that this metric is asymptotic flat. And of course it looks that. Yeah. Spherical measure, large R, derivative. Yeah. And that is, you want to evaluate this on something phi in. Looks like a plane wave. As R goes to infinity. And phi out, which of course is going to be some kind of spherical wave. Equations of motion. To solve, look something like v squared plus m squared phi is h mu nu. I've just split G back up into e to the h. Stop laughing at me. Okay. So, lightnings and scattering. We want to make contact with the iconal. This thing is still pretty hard to solve, right? In general, if I give you some arbitrary metric here, depending on x, arbitrarily, pretty much. Yeah, it's going to be tough to solve this. It's going to be a very unpleasant solution.
What is that? Is partial what?
What? Well, yeah.
No, the previous equation.
This one?
Yes.
That is the wave equation.
It's a new.
Oh, sorry, this bit, partial one. Yeah.
H.
Why isn't it a trace of H? I'm probably just ignoring it. Just to keep my life simple. Yeah, sorry, this is all a bit schematic. We go through all the details. Ask Tim. Okay. So what these guys do, not me, you try and solve this with an iconal kind of ansatz. Where's my... So you guess that your phi, the thing you're trying to solve for, looks like chi over h bar. And I'm just going to jump straight to the answer and write down what you get. This is the 2-point amplitude for scattering eta p prime, and it starts with a delta function, which conserves energy, which is what you would expect in a space-time where, you know, et is a killing vector. And of course, that just comes from having this integral over all times, appearing in the definition of the amplitude. And then you get some two-dimensional integral. They should all start looking very familiar. E to the I. I'm going to call it perp. P perp. P perp. And the I chi minus 1. Then should be familiar. Well, chi is, this is all kind of done to lowest order in H bar. Etc. 1 over 2p parallel the integral from minus infinity to x parallel z. Let me write it down and I'll tell you what it means. H mu nu x perpendicular z e mu. Right. So that looks rather like the iconal. Yeah. This function chi is just like a straight line segment, kind of, through the metric to your space-time. Z is Z and x parallel. That's the direction, that's the coordinate in the direction of P. Yeah. And then you've got two other transverse directions. Yeah. So x parallel is, you know, your initial. Go mad if my students wrote something like that, but there we go. You know what I mean.
Hey, hang on. I mean, shouldn't there be 4 variables in the H? Right, 3.
Second, sorry?
Yeah, it's dumb maybe, but X perp 2 or 3 dimensional.
X perp is two-dimensional
There are 4 dimensions living in H medium.
because H does not depend on time. It's stationary. Right, it's just a function of position. So that's why you've got this energy conservation over R. Yeah, Schwarzschild is your basic. Yeah, otherwise you would never get that. It would be more complicated. It's what this does. Kind of generalizes the iconal. For any stationary space-time. So it's like the generalization of, you know, the ladder resummation in the iconal regime, but now you're not thinking about scattering a scalar off a particle, but scattering off something, right? Some mass distribution, which are not specified. This is now some weird blob of stuff.
Or just a question, are you implicitly iterating the integral, or is it just first order post-Minkowski?
First order. Use first order. You can, well, it's not entirely, well, no, it is iterating, isn't it? Sorry, I'm confused. So that H, deviation of the metric from eta, you can put a kappa in there if you want, and then it's all orders. It's all orders in the sense that in the same sense that the iconal is all orders. It's resummed. Like the resummation of this guy.
Iconal function usually has an all orders power series in G.
Yeah. So there's a truncation happening, absolutely, but it's happening upstairs. Yeah.
So what you differentiate is order kappa, right? And because of the exponential, you carry things that are all orders in kappa. Yes, but you could only reproduce like the 1 p.m. result accurately.
I guess strictly speaking, yeah.
Yes.
Yeah.
So you're assuming linearization here, and it can be extended, but
It can,
you
but
haven't done it.
exactly. So the idea is there. You calculate the solutions, you evaluate them on the action, but just solving this guy is a complete mess. So you know, whatever perturbative expansion you put into this feeds through to the final answer. Yeah, exactly. Yes.
Let's assume I can solve this equation to higher and higher order.
Yeah.
Are you saying if I take this A and calculate the scattering angle, I have everything in there?
Yes, in this, effective probe limit, yeah.
Because I think here you get the problem and you never get one SF with this. Like you're not, you're
No,
not,
no, no, you're not getting any SF stuff here. No, this is probe limit, definitely, because it's background.
how would you go beyond static?
How do I go beyond static?
How do you go on SF?
So you want radiation.
Sure.
Yeah, then you end up calculating, say, the 3-point amplitude.
Oh, the one you had at the very beginning.
Yeah, exactly. Yeah, yeah. Yeah, you need the high point amplitudes. Start getting that stuff. Exactly. It's good. Yeah.
You want to go to one chef, then you want the recoil on the background metric that you have, classical background.
Yeah, so okay, fine. In my head, I often conflate cell force with like just background field with radiation reaction. Sorry. I really want the cell force stuff, then I've got to do something smarter than this. Because at the minute we're just treating the background as stationary fixed. So, yeah. Yeah, sorry, it comes from having like a QED background where people just say cell force and radiation reaction to mean the same thing. And of course, it's not. All right, very good.
The result is independent whether you're doing massive or massless geodesics. There is no.
There is no M here. This was all done for massless, I think.
Well, do you have a mass in the equation?
I do, but that might have actually been me being lazy. So.
Lazy. Needed to.
Because if it's massless, then I was wondering, shouldn't you fix the boundary conditions at square minus, so fix the advanced time and then look at the
Yeah.
retarded? I think you were taking T fixed and R to infinity, right here?
Yeah, exactly. However, maybe Sonia, yeah, no, Sonia might talk a little bit about this on Thursday. It still works to put your boundary conditions at R equals infinity, even for say the gravitons scattering on this space time. I agree with you completely. It seems weird, but it works.
Maybe another question,
Yeah.
you were saying in order to go to one loop, because then to check this exponentiation that you can put the sting upstairs, you should be able to, you have 1/2 factorial chi at one loop.
Yeah.
So what would be the prescription to do the one loop calculation? If any.
To do it kind of in this setup, you would need the one loop quantum effective quantum effective action rather than the classical action.
But don't I need to calculate like diagrams and amplitudes to calculate the one loop effective action? So then you're giving me a prescription to calculate the amplitudes from.
From the path integral. Right. Without going via the diagrams necessarily. Yeah.
Sorry, I'm confused. I mean, you need the one loop like the chi half. I mean, but that's put in here by the ansatz.
No, I understand, but then to check if it really.
You actually want to check it explicitly.
Just calculate blindly the one loop amplitude and check if the leading superclassical piece is one.
That's true. So the simplest way of doing it is, just to go away and calculate it all perturbatively in your given background and then just match it that way. It's the easiest thing to do. Yeah. All right. Cool.
What is the result? You have to integrate something, so there's. What's the result of the integral?
What's integral?
That's in your space.
It's in space time. I can't tell you what it is, right? This is completely arbitrary. So it is what it is. Typically, you're not going to be able to do the integrals. Well, you can do that one. Right? Probably can't do that one.
I don't like getting the 3-point amplitude, whatever theory you use.
Yeah, this is the thing with these background fields, right? There's just no universal answer. You can go further with some backgrounds than with others and get more explicit results or less explicit results, depending on how complicated the thing is. Unfortunately,
Yeah, but for instance, for Schwarzschild, since it's the probe limit, the Lincoln is known, and therefore the interval
So this you can check in the Schwarzschild limit, of course.
could be doable in that case, for instance.
Absolutely. Okay. So very briefly, how am I supposed to get bound state transitions from amplitudes? Well, this always makes me scratch my head. I mean by an amplitude when my final state is not free, right? I'm not certainly not scattering it. It's just that. Yeah. Presumably what you would end up doing, you have some two-body system, you'd calculate the two-body wave function, and you would use that to in some kind of matrix element, right? Finding two-body wave functions is awful. Because it's all much simpler in the probe limit, where you only have one body scattering off something. Again, this has been known for a very long time, right? You go away, solve the wave equation on Coulomb or Schwarzschild background. There are scattering solutions and there are bound solutions. Yeah. So you've got those straight away. How do you calculate transition amplitudes between them? Well, you've got this definition from the Perturbative method. It basically says, stick them into the classical action and pick the right term. And that should be the answer. So from that, you can read off some definition of boundary to bound matrix elements. So third prescription in this case, if you want to calculate a radiative transition from scattering to bound by 3, you need the piece of the action, which is linear in your incoming scalar, your outgoing bound scalar, and the radiation that it emits. Again, if you just think about some gravitationally coupled scalar, then d4x square root minus g, blah, blah. Again, let me write this out and I'll explain what's going on. Right, so we've got some background metric G, Schwarzschild, linear Schwarzschild, whatever you want. There it is. G. Sending in something. Yeah, free field in the asymptotic past. And I'm interested in the case where that ends up being a bound solution. And of course, if I want that to happen, then it is going to have to radiate something. And in this expression, H is what it radiates. So I'm using H for like 12 things. So that H needs to be scattered graviton wave function. Oh, sorry, we need to put labels on all these phis. mess. So this is just 3-point.
Needs to be a pi out as well.
Probably. Out, in, out, in. Yeah, thank you, very good. Yeah, exactly, so it's linear in each of the fields that you're scattering. Very good. Yeah, so you solve your wave equation on Coulomb. In is your incoming guy, which looks like a plane wave in the past. Out is your outgoing guy, a kind of spherical wave. Sorry, not spherical wave, a kind of bound state solution. And H is some scattered graviton solution. And it's an absolute mess to calculate this. Okay, again, maybe Sonia will say something about not the bound state calculation, but related 3-point calculations in context of waveforms tomorrow. But you can ask, you know, is this perturbative thing really giving me the right answer? Yeah, you can check using Dyson and beta saltpeter. This thing really does spit out what you expect, the scattering to bound transitions. Ricardo talk about that today. Yeah, today. Okay, good. Bound state this afternoon. All right. Very good. So you can use this perturbative approach to do scattering to, so boundary to bound transitions if you want. And some limits in some cases you can check, starting from the full 2-body picture, that it really gives you something sense.
To get the phi out, I guess you have to solve the wave equation when the particle is going in, or
No, sorry. So phi n is solved with a condition that it looks like a plane wave in the past. And then you let it go. All right. This guy is one of the bound state wave functions of the Coulomb equation. Yeah. Good. So that probably is worth emphasizing in this case. So this is the horrendous hypergeometric 1F1 thing. It's linear Schwarzschild. And this is some Laguerre polynomial with an exponentially damping R thing. It's really about so. Yeah.
you solve it in a near horizon limit or something. So I mean, otherwise there is no solution.
Linear Schwarzschild. Linear Schwarzschild. All right. And the final example. A couple of lines. Of what you can do with this perturbative method. Go back to my nice safe space. Having a lovely wave. Oh, right. So there's some kind of wave. I suppose that I send in nothing. Then there is possibility for this guy to produce particles, which often goes under the name of the Schwinger effect. And William, we'll talk about that on Thursday. All right. So the Schwinger effect is cool because it's a genuinely non-perturbative phenomenon, or rather it's got non-perturbative bits in it. There's a particular kind of class of electric fields in QED which behave a bit weirdly and which do produce pairs in a very strange way. And we'll talk about all of that. We'll talk a bit more about pair production in half an hour using world lines. All right, I think we'll stop there.